Okay, I just, there is one remark I have to do, something I have to say about yesterday's lecture. And so I show computation about the first variation of the area, and at some moment I said we need the surface to be codimension 1. Actually, that was true only for the last part of the computation. So that was the fact that the first, this so this identity, well, using Yoshi's notation, the tangential for the divergence, this one didn't use any requirement on the codimension. So this was true for every dimension and codimension. It was the second part where I started to write this in terms of mean curvature, that one. I was using the fact that we were in codimension 1. Okay, so till this formula, I use basically only the area formula. Okay, so this said, today I would like to begin with a short review of the possible approaches to existence results for minimal surfaces. Okay, so most approaches to existence of minimizer of variational problems are based on the so-called direct method in the calculus of variation. So let me, and the direct method is simply a complicated way to say that they are based on semi-continuity and compactness. Okay, so this is how you prove most of the existence results. And okay, so what is it? When I say semi-continuity and compactness is a shorthand for trivial observation, which is the following. If f is a lower semi-continuous function on a compact metric space, then it admits a minimum. Okay, simply, well, metric space is not important, but let's say if you are in a metric space, okay, what you do, you take a minimizing sequence, so a set of point xn such that the value of f at these points converge towards the infimum of f. Then by compactness, xn will converge up to subsequence to something. By compactness. And then by semi-continuity, f of xn will be less than or equal than the liminf of this, which is the infimum. Okay, and so you prove this is a minimum point. Okay, so that's obvious remark from analysis 1, maybe. And the only thing is that when you apply it in a practical situation, you won't have really a compact metric space, but the only things you really need is a compactness for minimizing sequences. Okay, so what you actually need So you don't need X to be compact. But good compactness for minimizing sequence is enough. Clearly, because that's all we used. And now the typical example of this is which is somehow the beginning of the story, is for the Dirichlet energy. So what we know is that the classical example is this one. You take this, okay, and then you take X to be the space of function in the sublet space W1T of omega. Okay, so the domain omega, and maybe you prescribe a boundary value. And so this is a given boundary value. Okay, and now you run exactly this approach. So it turns out that F is lower semi-continuous with respect to the L2 norm, L2 distance, and that you have compactness of minimizing sequence in L2. Are compact in X. Again, with respect to L2 distance. So essentially, you take this space, you put L2 distance on it, and you are okay. So maybe that's not the most elegant way to put it if I want to make a full. But what I'm trying to point out is that the typical example is you have a semi-continuity with respect to, if you want a weak topology of W12, if you really want to be precise, but let's say in this case it's equivalent to say you are lower semi-continuous with respect to L2, and you have compactness in L2. And in some sense, that gives you existence of minimizer, okay? And then how the story goes on is that you use regularity theory to prove that minimizer are not W12 function, but are are smooth. Then regularity theory gives that minimizer U bar are smooth. Well, okay, and so our harmonic functioning, by the way. Okay, so this is the typical scheme, right? And that's the simplest case of this. So one thing is that I want to attract your attention is that, well, one of the trick in this approach is that you have to construct a space and a topology on this space in a sense where you have both lower semi-continuity and compactness. So for instance, this approach wouldn't work if you just take C1 function, because you have lower semi-continuity if you want, but you don't have compactness. So that's why you have to enlarge the space of admissible function from C1 to W to the Sobolev class, because there you have compactness. And then in the end, forget it, because in some sense you have regularity theory that gives you a smooth function. But somehow in the middle, at some moment, you need to work in an enlarged class. Okay, so that's how it works. And the interesting part about the area functional somehow is that it doesn't quite fit this approach. So, and it's for a reason that makes it very interesting in some sense, not because of pathological or in some sense irrelevant reason, okay? So what I will do now in some sense is try to explain why there are the possible approaches to the existence of minimizer for the area functional. And most of them somehow try to follow this kind of general scheme, but it don't quite work. Okay, one of the reasons is, well, there are several reasons. The first is, in this approach, you can see it here. If you don't have subbolus spaces, you are in troubles. Okay, because this approach cannot work without subbolus space. So in the end, you get that the minimizer is smooth. But first you prove existence in an enlarged class. Then you go and prove regularity. Okay, that's the power of this method, right? But so the problem is that you have to construct enlarged classes where you have compactness. And that's the first problem when you're talking about surfaces. Okay, what are the classes of enlarged classes of surfaces where you have compactness? Okay, that's the first problem. But then there is a second problem. Regularity theory works fine for certain problems, not for minimal surfaces, okay? And the reason is that minimal surfaces in general will not be regular. Let me be more precise. I will give examples, but essentially the simplest example is there are nice curves in R4 such that the minimizing the surface of minimal area with that boundary has a singularity. It's not a smooth surfaces. And what I mean by this is that whatever minimizing sequence of smooth surfaces you get, it will converge to something which is clearly not a surface in the smooth sense. So here is not a matter of which framework you choose. I mean, you can start from the most regular object in the world and take a minimizing sequence in this class, and they converge to something which is not smooth. So, I mean, this is not a lack of regularity which is due to the class you work in. It's real, okay? And so this is exactly one of the problems. Regularity theory doesn't work. So this means that once the way you decide the class, you enlarge the class of admissible surfaces in order to get existence of minimizers, but you don't get back to the original class of smooth surfaces. So this means somehow that the way you enlarge the class of admissible surfaces will be relevant in the answer you get, because you will not get back to smooth surfaces, okay? So it's not like this perfect story where you introduce this, but in some sense you forget about it after a while because you get a smooth answer, right? So it's really a more delicate thing. So the way you enlarge the class of admissible surfaces is also plays a role in some sense, affect the answer, okay? And so I will now very quickly tell you what are the, well, I will try to give review of what are the existence approaches, the approaches to existence. And I will start with the classical one due to Douglas and Radot. So the first approach sorry, I'm saying existence to minimal surfaces. I should say solution of plateau problem, okay? And this is Douglas, Radot, and somehow other people optimize it later, okay? It's a very nice approach, gives probably the best results possible, but it only works in dimension 2. Where D, I remind you, is the dimension of the object we are considering, of the surfaces, okay? N is the dimension of the ambient space. Okay, somehow, let me first start with a remark about a trivial problem, which is that of geodesics. So if you want the plateau problem in dimension 1. So before going to that, a little detour. Geodesics. What I mean by that, okay, that geodesic is now becomes the curve of minimal length connecting two points, well, not in Rn because that's a segment. Okay, so let's say to make the problem interesting on a Riemannian manifold. Otherwise, the answer is trivial. Okay, so geodesic equal curve of minimal length connecting 2 points on a Riemannian manifold, on a surface, okay? So that's my definition of geodesics, means a minimizer. And if you take any book in differential geometry, curve, sorry, let me first specify what I mean by curve. A curve for me is a map from the interval 0, 1, also called I, into M, okay? Okay, if you take a book on differential geometry, you will find out that the equation of geodesics, that is the Euler-Lagrange equation that defines geodesics, is not the Euler-Lagrange equation of the length functional. It's the Euler-Lagrange equation of something else. So essentially, geodesics equation is the Euler-Lagrange equation of the following functional, E of u. Okay. Let me just be, so what is u dot? You have a curve on a manifold. At every point of this curve, u dot is the speed of the curve, which is a vector tangent to the manifold. Since the manifold is Riemannian, to every vector in a tangent space, you can define the norm. This is the norm of that vector. You square it and you integrate. Okay, so, but this is the point. When you take the, what geodesics are for people in differential geometry is they are solution of the Euler-Lagrange equation of this functional, which is not the length. Okay, the length functional length is okay, so how it comes, these people minimize the wrong functional. No, of course. They don't minimize the wrong functional. But there is something interesting here, which works also for surfaces. And that's somehow what I wanted to point out. So let's see what happens with curves first. And the point is the following. There is a first remark is that, well, this functional is always larger than this one because and now by Jensen inequality, you get this. Okay. But then you see immediately, so this functional, the E of u is larger than the square, of that functional. And then what you realize immediately is also that the identity holds if and only if dot, the modulus of u dot is constant. So if you have a constant speed parameterization, okay? And the second remark, which is obvious, is that, well, whatever curves you take, you can always find a constant speed parameterization by just reparametrizing I. So for every u from I to m exists sigma homeomorphism from I to I such that the composition has constant speed. So satisfies exactly this. Okay? And now if you put together these two remarks, okay, now I did it, yes. I will put them together here, presumably. So what we get is that if I take, okay, if u bar is a minimizer of E of u among all curves with the prescribed boundary, okay, with the prescribed values at the boundary. Okay, we are talking about connecting two points. So among all admissible. Then you have the following, that then for every u, which is not this one, you get the following, that the length of u is equal to the length of u composed sigma, well, that sigma here. And the reason is that the length is independent of parameterization. So you reparameterize, if you reparameterize u by composing with anything, any map from any homomorphism from I to I, the length will remain the same because it only depends only on the image, right? Okay, but then this is equal to the energy of this because this specific parameterization, I mean, is a constant speed, so we have equality with the energy. But then because u bar is a minimizer, you get this. And this is larger or equal than the length of u bar. So what do we get is that u bar is a minimizer of L as well. Because this is an arbitrary u. So u bar minimizes so actually they didn't got the wrong problem, right? In fact, it's better because by minimizing E instead of U, you not only get a minimizer, but you also get a minimizer with constant speed. So if you want, better parameterization than others. Okay? And it has constant speed, velocity. Okay, so somehow among yes, sorry. Thanks. And no. Okay, sorry. There were the inequalities involves E and the square of L, not. Thanks. Okay, so that's an interesting fact. You don't really need it. But for instance, let me notice that if you want to minimize E of u, then you are in a Sobolev space. That's not difficult to be done. Okay, there are infinitely many ways of doing it. But if you really minimize this as it is written, you would go in a space of BV, which is more complicated. So let's say that this is interesting. Now, the interesting part is that something like this works also for surfaces, but only for surfaces. Okay. Now we talk about surfaces. And so first of all, let me explain. So you try to do the same for surfaces. So what is a surface for you now? It's two-dimensional surfaces in Rn is something you parameterize by a map U. Maps from a reference domain in R2. So they are maps from a reference domain in R2 to Rn. Reference domain in R2. Okay, so by the way, this is called the parametric approach to minimal surfaces. It means that you don't see surfaces as objects by themselves, but as sets parameterized by U, and you think about U as a variable rather than the set. Okay? As you usually do with curves, right? Usually curves are not their image, but they are maps. Okay, so in the parametric approach to minimal surfaces, you consider surfaces as something parameterized by a standard domain in R2. So for us, this will be the disk, the unit disk. This disk with C or K when we are in geometric setting? Disk, well, both. Okay, so let's say we start and we want to minimize. What is the area? The function you want to minimize is the following. Well, it was the area formula. We gave it yesterday. It's simply the following: is the integral of take the two partial derivative of U, take the exterior product, and then you integrate the norm of this. And okay, if you are in R3, this is just the standard vector product in R3. Okay? That's what I said yesterday. This is the area of this. So that's what you want to minimize. Okay? And you want to find a minimizer of A of U with prescribed boundary values. Let's say U equal to a certain given gamma on the boundary of D, where gamma from the boundary of D in Rn is given. Okay? So that's the minimal surface, the plateau problem. Okay, now what happens if, first of all, what happens if you try to minimize this? Well, one say, why don't we try to apply the direct method? Okay, this looks like a functional, which may be not the Dirichlet energy, but not too bad. And what fails now is not, so to apply the direct method, you need semi-continuity and compactness. What fails here is not semi-continuity. That function is nicely semi-continuous. What fails is compactness. So if you try okay, if you try the direct methods, semi-continuity is okay. Compactness fails. Oh, wait a moment. Before talking about compactness semi-continuity, I should tell you what is the space, right? And what is the topology. Let me be more precise. When I say semi-continuity is okay, means whatever space you would like to imagine of Sobolev type, you have the semi-continuity with respect to the weak topology. Okay? So I'm not entering into detail, but let's say Where is this functional nicely defined? Certainly in W12. Okay, because this would be in L2, this would be in L2, product of L2 function is in L1, so you can make the integral. And it is weakly lower semi-continuous. Okay, so if you have a sequence UN which converges to U, then this in W12, this will converge. So in some sense now, without entering into details, I'm simply telling you this won't be a problem. Okay, of course, the answer depends on which space you choose. I'm saying that that's whatever space you choose, reasonable one, you won't have a problem there, but you will have a problem here. And now to show that compactness fails, let me give an example of lack of compactness. And I'm not telling you what the topology is, but you will see from this example that whatever topology you choose, you do have a problem, okay? So in some sense, the example of lack of compactness is independent of the topology because shows something goes wrong. And the reason this fails, because you can always find a minimizing sequence UN such that it converges to a constant function. In the interior of the. Well, then this has to be bad, right? I mean, you start from surfaces, and the limit is a point. Okay, so this must be, there is something wrong, which is really wrong. This doesn't depend on which topology you choose. I mean, this is the bad lack of, and a serious lack of compactness. Okay, and why so? Well, the reason is simple, is that start from any other minimizing sequence. Choose an arbitrary minimizing sequence, Vn, and then define okay, let me be more precise. And then define UN just as a reparametrization of Vn, where sigma n is an homomorphism from D to D, which has the property of taking a large part of D into a very small ball close to the center and somehow leave and use the rest of the annulus to cover the. So it's an homomorphism such that sigma n maps the small ball of radius epsilon n center in 0 disk, okay, onto a large disk with epsilon small enough. Of course, I can always construct an homomorphism of the disk that take a very, sorry, the other way around. Wait. I can always take an homomorphism that take a very large disk centrally and maps into a small one. Okay, that's not a problem. But if I do this, what happens is that if I look at this map here, and I look what values takes on this ball, well, will be the values taken by Vn on this very small disk. So in particular, if this is really small, I can assume that Vn on this small disk has almost constant value. So what happens is that Un takes almost constant value on this large disk. Well, the limit will be a constant. Okay. And so here is a problem. And where is exactly the problem? Oh, yeah, there is something I should add. that UN is still a minimizing sequence. So UN converges to constant and is a minimizing sequence because the area functional is invariant under reparametrization, right? I mean, it should be the area of the image. So because A of UN is equal to A of Vn. So if this were a minimizing sequence, this is a minimizing sequence as well. So what happens here is that you see that the area functional is invariant with respect to a group of transformation which is a bit too large. So the group of transformation being the reparametrization, okay, which is a bit too large, and the fact it's large gives you a lot of non-compactness, okay? So that's the problem of the area functional, which of course doesn't happen with the Dirichlet energy. The Dirichlet energy is invariant under very few, transformation. Okay, and so how do you fix this? And that's the Douglas-Radeau approach. The way you fix this is simply by minimizing another functional. And guess what? You minimize the Dirichlet energy. Well, I think I have to delay this, even though in the end it will be the same story. So now let okay, that's the Dirichlet energy, way better than the other one, because for the Dirichlet energy, compactness is not a problem. Okay? Well, there is a trick there. But anyhow, let's say what happens here, and now I follow exactly what I said before. So the first thing is the two functional are related. And the relation is the following. A of u is this integral by definition. Now, whatever notion of product you take, if it is a reasonable one, certainly this norm is less than the product of the norm of the two vectors. Well, in the case of the vector product in R3, you know it, because the norm of this product is the product of the two vectors times the sinus of the angle in between. Okay? So it's certainly less. But this is certainly less than Dirichlet energy. So the area functional with no square is now less or equal than the Dirichlet energy. Okay? And you have equality also. If and only if, okay, what do you need to have equality? You need equality here. Well, this is the inequality AB less or equal than 1 over 2 A squared plus B squared, and you have equality only if A and B are the same. So first you need to have equality here. You need that this two vector has the same length. Everywhere. And then you need equality here. Now, if you think about the vector product in R3, the norm of the vector product is given by the product of the norms times the sinus of the angle. So the only case of equality is when the angle is 90 degrees. But this means that the gradient of U is a so-called conformal matrix. Conformal matrix means that the associated linear map preserves angles. Or if you want, more concretely, it's an isometry composed by a dilatation. Well, something like that, okay? So it preserves up to a constant, preserve the scalar product. Okay, so it's a very nice map. So here it is. You have identity if and only if U is conformal. Let's summarize here. Holds if and only if U is conformal. Which means, again, that the gradient of U is a conformal matrix at every point. Okay? So this is the first fact corresponding to the first fact in the previous discussion, in the one-dimensional discussion. Then we have, so corresponding to this. Now we have a second fact corresponding to this, which is exactly the same. Every map can be reparametrized so to obtain a conformal parametrization. Except this is a trivial statement. The two-dimensional one is known as Liechtenstein's theorem. Is not that trivial. So, Liechtenstein's theorem says the following: for every U from D to Rn exists sigma homomorphism of D such that U composed sigma is conformal. Okay, this is Liechtenstein's theorem. Which is not that trivial. By the way, you can prove in many ways. The two-dimensional version of it, so if you had, let me quickly say that, just to give a feeling about this statement, if you have never seen it before. If the map were valued in R2, not in Rn, so, well, that's not the case we're interested in. But in that case, conformal maps are either holomorphic function or anti-holomorphic function. And this statement is somehow retelling the fact that whenever you have a simply connected domain in R2 in C, which is not C altogether, then it's holomorphically equivalent to the disk. Okay, that's Riemann theorem. Liechtenstein's theorem generalizes it to surfaces in Rn. Okay, so this is a non-trivial theorem, but once you have this, you can run the same program as before. But then, well, well, let's try to put it here very quickly. If U bar minimizes E of U, not the area functional, but the Dirichlet energy among all admissible U, then, as before, you get that it minimizes also the area functional. Because take any U, any competitor U, the area of U is equal to the area of U composed sigma, this one. You use this theorem. But this is the same as the Dirichlet energy of U composed sigma. But this is larger or equal than E of U bar because this is a minimizer. And in turn, this is larger or equal than E of U. And now there are no squares, okay? No, just to be. Okay, so same as before. And this is the core of Douglas' approach. 2 remarks. I'm cheating on one point. And well, I'm cheating. I've not been precise on one point. And the point is all admissible U. Well, here I said what are admissible U? Those that exactly take the value gamma at the boundary. It doesn't quite fit with this theorem because I didn't say that this homomorphism is the identity of the boundary. When I apply this homomorphism, you still map the boundary onto the boundary, but not identically. You're changing the boundary value of U. Okay? And it doesn't work otherwise. I mean, it cannot work with requiring the identity of the boundary. If you want, because, well, for a holomorphic function, you know, an holomorphic function which is the identity on the boundary of the disk is the identity everywhere. Okay? So this means that we can't minimize on the class of U with given boundary, but we must minimize on the class of U with given boundary up to reparametrization, which, of course, geometrically is fine. I'm simply saying that the image of U of the boundary according to U is the usual curve. Simply, is not parameterized as the parameterization is not given by gamma, but it's a reparametrization of gamma. Okay, so this gives you a slight problem because one thing is minimizing the Dirichlet energy with prescribed boundary. One thing is minimizing the Dirichlet energy with this weaker notion of boundary condition, this weaker boundary condition, okay? So there is a technical difficulty there, and part of the work of Douglas was exactly to go over this difficulty, okay? So it's not as tame as I told the story. And Liechtenstein theorem is not completely obvious, okay? And then, okay, this is one remark, so there is some work to be done. It works fine for the disk, so if you prescribe your model of surface is the disk. If it is more complicated, like a disk with a hole, like an annulus, or a disk with a handle, then it becomes more complicated because the story is that, how do you say, the conformal class of the disk, there is only one conformal disk. Okay, so all disks are conformally equivalent, but not all surfaces are conformal equivalent. Okay, the description of conformal equivalence of surfaces goes through, there is a characterization, and it's always more complicated than that. The only case of a surface which is, there is only one type of conformal class is the disk. In all other cases, you have to work harder. So by the way, Douglas did also the other cases, but they are considerably more complicated for this reason. Okay, there's a geometric reason if you want. And why does this approach work only in dimension 2? It works only in dimension 2, well, you have an inequality like this also in higher dimension. Here we will get the product of 3. Okay, you put 3 moduli here. Let's say you are in dimension D. Here you get the product of D vectors. You put the product of the modulus. And here you put not the Dirichlet energy, but the du to the n, to the d. Okay, so you have an inequality like this. But the problem is that, again, equality would also hold for conformal maps. But conformal maps in dimension larger than 2 are very few. So the conformal class is rich enough, the class of conformal transformation is rich enough in dimension 2, but it's extremely poor, it's extremely rigid in dimension larger than 2. So what you would miss is the equivalent of Liechtenstein theorem. That's not true. And so that's the end of the story. People couldn't go over it. But keep in mind, the best possible results in terms of regularity, description of singularity, and so on, you get with this theory. Okay? So the two-dimensional theory done this way gives you really, in some sense, the best possible results. Okay? Because in the end, you have a parametrization which is close to, is a conformal, which is close to be holomorphic in some sense. You really get a very good parametrization of your surface. Okay?
But even if you were able to overcome that one portion or not, then you wouldn't get regularity because you don't get an elliptic problem.
Well, but at least you will get existence, but not even in any case. No, here the problem was, let's get to existence at least. But no, well, yeah, okay, so the amount of problems would be infinite, actually. Nothing would work. Okay. So that's why this approach is confined to dimension 2, but it works really well there. And, okay. Should I go directly to the end? It's 1 hour and a half, right? Asking.
Maybe I just have just one question. So you have regularity for you, but it doesn't mean regularity of the image.
No, the image will be self-intersecting, by the way. Okay, so, I mean, this was just to sketch what you can do in dimension 2. There are many things. Okay, so you will be regular because it's conformal and it's nice. But of course, the image will be self-intersecting, possibly self-intersecting. Okay, that's nothing. So if you take this boundary value, a disk where some handle comes out, so this is a curve I'm describing. It does like this, and then goes down here in the middle of the disk and goes this. And so the minimal surface you get with this approach will be essentially this one. This disk here will be self-intersecting and reappearing down here. That's for obvious reason that it's not much else you can do. Okay. And so it's a complicated story comparing the results you get in one area and the other. And okay, maybe we take a really 5 minutes break. So, okay, this was one approach about finding minimal surfaces. Then there is a second approach, which is somehow interesting. It says, well, let's consider surfaces just as sets and take limit of sets, no parameterization, no. So why not try the most direct approach? What are surfaces? Sets in Rn. Okay. So second approach. This is non-parametric in the sense that, again, I don't view surfaces as parameterization, but just as sets. Surfaces just as compact sets, let's say. Well, now one could start thinking, well, why not? After all, there is a good compactness theorem for compact sets. That is, if you have a sequence of compact sets in Rn, which are uniformly bounded, then up to subsequence, they converge in the Hausdorff distance. Why not? Why not use that? What would be the problem? Of course, you cannot, right? I mean, otherwise we wouldn't be here discussing this problem. But let's see why not. Okay, so try to use compactness for sequences of compact sets given by Hausdorff distance. Okay, now you easily have compactness. Well, the first problem is that the limit of very smooth, nice surfaces in the term of Hausdorff distance can be a disaster. Okay, first problem. Okay, so, well, you would have compactness, but you would have compactness in the class of compact sets, which includes surfaces, compact surfaces, but also a lot of other things. Okay, so that would be the first problem. First issue. The limit could be bad. One would say, well, but the real problem, or if you want, is the same problem told in a different way. You don't have semi-continuity of the area. So second issue. Area is not lower semi-continuous. What I mean is that if you take a sequence of compact set which converge in Hausdorff distance to a Cn, say, that converge in Hausdorff distance to a compact set C, the Hausdorff measure is not lower semi-continuous on these sequences, okay? And let me give an example, not just of lower semi-continuity, but exactly what could go wrong taking minimizing sequences of a plateau problem. Okay, so not just failure of semi-continuity, but really now I'm considering minimizing sequence for the plateau problem. And somehow the example you have to keep in mind is the following. Let's say this is your boundary in R3. So two surfaces, D equal 2 and N equal 3 if you want. So your boundary datum is a circle. So, well, you know what the minimal surface must be the disk. But let's say you pretend you don't know that, and you can construct a very wild minimizing sequence. Of course, I mean, forget the fact that you know what the minimizer is, okay? The problem is what happens to minimizing sequence. And the very wild minimizing sequence is the following. Well, you start from the disk itself, which is already the minimum, but for the sake of argument, then you modify it by adding a bump into it. Let's say a very small bump. Okay, so this would be sigma 1, the first surface with given boundary gamma. Then the second surface, you make a similar bump, but you make it thinner, and you start branching in it. So this would be sigma 2. And then you go on like this. Sigma 3, you will make an even thinner tube coming out of it, but with more branches, okay? So this is really a surface, okay? It's not, I mean, if I enlarge this here, I see something like this. So it's really a surface, okay? With, I mean, in the topologies that, I mean, these are smooth surfaces, simply very thin. Okay, then it's clear that what I can do this way is produce a sequence. Of course, I mean, how much area do I need to construct this extraction? I don't know how you want to call it, this wrong parts, if you want. I mean, as small as I want. In the moment they are thin, I mean, the length of all these branches can be a lot, but if the length is L, the total area is L times R, the diameter of this tube. If I choose R small enough, length times diameter will be as small as I want. So I can do this addition with as small area as I like. So in particular, I can produce a minimizing sequence of this, because the area of these surfaces will be the area of the disk plus something that goes to 0. But the limit of this, in the sense of Hausdorff measure, can be the entire space. I mean, these things start branching, can go everywhere. Okay? So, sigma n minimizing sequence, but Hausdorff limit equal R3. It's really bad, okay? So here is the problem of, if you try, why not, to work directly with sets. What is the problem? Well, that's a typical problem, okay? So, of course, one would say here, well, that's not a real problem because I did something artificial. I started from something very good and I make it worse. But that's exactly what you don't know, right? I mean, so what I'm saying is that if you take an arbitrary minimizing sequence, it can be really bad. Now, actually, people, well, not people, one person made it work. And this is, I think, Reifenberg, in a sense, made it work. however, see the work of Reifenberg. Just good to give a little bit of dates. Douglas, the approach I described before, Douglas and Radeau goes back to the 30s. Reifenberg goes back to the 50s, late 50s, maybe beginning of the 60s. Okay, early 60s. Okay, and okay, I can't say, I mean, that's a non-trivial approach, but essentially what he says is that, okay, yes, of course, if you take an arbitrary minimizing sequence, the limit can be a disaster. But you can, in some sense, nobody tells you that you have to start from a bad minimizing sequence. But certainly, there is a problem in this approach, means that you have to select the minimizing sequence properly to clean it out, and then you can produce something in the limit, which makes sense. So, but this means this is a hard approach. Because it's not based just on a simple compactness and semi-continuity argument, okay? It's really hard. And anyhow, it was made to work. By the way, that's not the end of the story. For some reason which this kind of approach, just look at the limit of sets somehow, or improve them or whatever, has been somehow carried out in more recent times with other results by several people. And so this is not, I mean, this story started with Reifenberg. Then essentially what happened is that he had a very nice result, existence for minimal surfaces. He died, and somehow the results were not forgotten, but close to that. And in recent years, many people started working on it again. Where, I mean, an approach where you say, well, I forget about abstract structures, blah, 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 no parameterization, no currents, no finite perimeter sets. I just work on convergence of sets and see what I can do, okay? Okay, now, there are many people working on this, so I will not give a list here, but since I'm simply saying that this approach is not that, but it's an hard approach, because it's not based on any easy compactness argument. Okay, there is no such an easy compactness argument. And now, quickly, what are the remaining approaches I have in mind? So the review will be finished then. And the final approaches is, let's call it the distributional one approaches. And so this will end the review. Okay. Last. Okay, let's say distributional non-parametric. And R essentially goes under two possibilities. The first is finite perimeter sets. And the second goes via current, integral currents. Okay. Concerning finite perimeter sets, the theory essentially is due to, well, it was inspired by Cacciopoli in terms of a definition, but it's essentially due to De Giorgi, while the theory of integral currents is due to Federer and Fleming. Okay, what I will spend the next lecture to explain this approach. I will not spend time on this because it requires a course by itself, the theory of currents. But let me tell quickly what is the approach, why I call them distributional non-parametric. So what both theories do is to enlarge the class of admissible surfaces, okay, introducing somehow in a different way some kind of generalized surfaces which essentially have the property of have good semi-continuity, to have good compactness properties. Okay, so what both people did somehow is to enlarge, to consider some class of generalized surfaces which has good compactness property, where the area functional is lower semi-continuous, and therefore you can prove existence by lower semi-continuity and compactness. Okay. This theory is almost a subset of this one. So this theory only works for d equal n minus 1. So what will be surfaces in this theory are n minus 1 dimensional objects, okay? I mean, that will be a generalization of n minus 1 dimensional surfaces, actually boundaries, okay? While here works in any dimension. Okay, so this theory is essentially a subset of this. But there is an advantage with this theory, is simpler, okay? So the main compactness theorem here is, if you want, well, that's trivial if you want, but saying the main theorem here, which describes the structure of this strange object, is a corollary of one of the theory here, of the rectifiability theorem of Federer and Fleming, but it is easier to be proved here. So that's why I choose to focus on this, because it's an easier theory, okay, rather than this one. This one requires a lot of... And why I called it distributional, because in both cases, the idea is to extend the notion, to generalize the notion of surfaces very much in the same way as Sobolev function generalized the notion of C1 map, C1 function. That is, via a distributional definition of derivative in that case, you extend from C1 to larger classes that have compactness property. Here is very much the same, okay? So you use, behind this, there is an idea of distributional boundary or whatever, and that's what is used to define these generalized classes, okay? So advantage is that you get easy, well, not so easy maybe compactness theorem. Disadvantage is that, okay, then you want to prove regularity, and the trouble starts, okay? So actually, but as I said, regularity for minimal surface is always a problem, in the sense that the answer in the end cannot be that the minimal surface is smooth in general. So it cannot be, there cannot be easy regularity theory, okay? And I think Camillo De Lellis will speak about the regularity theory for integral currents in the next week, okay? So, in the time remaining, which is very little, I wanted to start with rectifiable sets again. Okay. I plan to be faster, but okay. So by the way, that's it for the introduction to minimal surface part of the course, okay? So that was the first half of the title, that's over. Now we talk about finite perimeter sets. And now to define these finite perimeter sets, we need some tools, and the first one is rectifiable sets. And now I will stick to the definition given yesterday. A set E in Rn is de-rectifiable, well, countably to be precise, but the countably will always be there, and I will drop it in the following. We will not repeat countably every time. If it can be covered by up to a null set, HD null set, it can be covered by countably many surfaces of class C1. So let me write in a slightly different way. If it can be written of union of sets EI such that E0 as measure 0. So this is the set you don't cover with surfaces. And EI is contained in MI surface, D-dimensional surface of class C1. Okay? And now there is another property I would like to add to this that was used in yesterday's talk quite frequently, and this, so I will assume from now on, it's not in the definition, but I will assume it, is that these sets have locally finite measure. Okay? It's not in the definition, but it's in a standard assumption. It was also a standard assumption in most of the statement yesterday. Maybe all? Actually all, probably. We assume that, so HD of this set intersected with any ball or any compact set is finite. So locally finite measure, because that makes them slightly better. Okay. And so one of the points that Yoshi put it out, explained yesterday very clearly, is that these sets can be a mess, but nevertheless they still have a notion of tangent space. And I will give you more details about that. So, okay, maybe I will take a few minutes beyond, sorry. Okay, there are two remarks. First, nice example of one rect. Oh, everything is Borel. No, that was, no, everything is Borel here, okay? We don't want to worry about, yeah, sure. No, even better. No, we don't want to worry about measurability. So let's say everything is Borel, okay? Nice example of one rectifiable set, the one that people have in mind, this one. Okay, but what is a bad example? So when you want to think about what properties these sets might have, you have to keep in mind some bad example, not just the nice one, otherwise everything is obvious. And the bad example you take the union of a dense family of segments, of a sequence of segments of length 1 over 2 over I, which can be summable. So let's say to make it even more complicated, you take this union where this is a segment with extreme xi, the other extreme vj, okay? Okay, so the length is 1 over 2 I plus j. And this xi you take dense in Rn, and the direction vi, dense vj, sorry, in S in the sphere. Okay, so let me see. This set is clearly rectifiable because it's a union of segments. It has finite length because I just choose this constant here, so to make the length summable. 1 over 2i plus j, sum over all I and j, you get a finite number. Probably 1, something like that. If you take a picture, though, you see a real mess, because not only this set is dense in the space, but whatever ball you take, it will contain positive measure of this set inside. Not only, if you also try to figure out, okay, what is the direction of this set at a certain point, there is something not obvious about it. Because if you look at this, it will look like for every xi we'll have segments going out from that xi in all directions, well, in a dense family of direction. And then this will be repeated for other xi, adding a dense some sort of dense family of this object. Okay, so when you take the union of this, it's really bad. Okay, so this is the bad example. There is another fact you want to keep in mind, is that one might guess, okay, are there sets with finite HD measure which are not rectifiable? And the answer is yes. So not all sets with finite HD measure are rectifiable. Okay, there are unrectifiable sets not rectifiable with finite measure. Well, of course, the plane is not one rectifiable because you cannot cover the plane with countably many surface curves, but that's an easy example. The question is whether it's a matter of measure. So is that a set with finite length, is it necessarily rectifiable? Answer, no. There are E which are not sets, not one rectifiable with finite length, and the example is the following in the plane. So keep in mind, things can be really non-rectifiable, even if the length is finite, and you start with a counter type construction, you start with the square of side length 1. This is the first step in your counter type construction. The second step will be 4 squares with side length 1/4. And then you can guess the next construction will be 16 squares with side length 1/16. Okay, and now you take the intersection of the union of these squares, blah, blah, blah. You get a set C. By a covering argument, you see immediately that H1 of C is finite. What covers do you use? Well, the squares. Okay. Actually, if you talk about square root of 2, I think, if that's the diameter of the square. Okay. By covering argument. Then you want to show that this is not rectifiable. Actually, it's not rectifiable in a very strong sense. Whatever curves you take of class C1, the intersection with the set will have length 0. So there is no way to cover all of these sets with curves. Class C1. Why so? Well, curves. Well, you can reduce by decomposing a curve in different pieces to graphs of C1 function. Okay, so every curve can be covered by graphs of C1 function. Either a function y function of x or x function of y. So you can reduce to graph. Graph of f of g. Okay, and since the set is symmetric, it's enough to prove it for a graph y equal g of x. And now simply you see, well, you look, what is the length of this set? Well, you can use the area formula if you want, or the usual formula for the length of a curve. The length of this set will be the integral of g square root of 1 plus you use the usual formula on the projection. Right? That's what it should be. That's the area formula if you want. And now you get 0 because these sets, the projection of this set is contained in the projection of C, and the projection of C is a Cantor type set of clearly length 0. Okay? So this integral is 0 because this is a set of Lebesgue measures 0 in one dimension. Okay? And there is one thing which is left to check. Well, it could be that this set has length 0, so I did cover it after all. I mean, it could be rectified. Every set of length 0 is rectifiable because I've allowed this in the definition, okay? So I should prove that this set has positive length. I didn't prove it. And the way you do it is that you notice that this set has a bad projection vertically and horizontally. The projection is a very narrow set. But there is one projection that gives you a full segment. And the projection is exactly the one which you project on this line. Okay? If you project on this line, you will realize that the picture is not. The picture is far from being perfect. But anyhow, if you do the right projection, you will realize that these four squares project in such a way that their projection are just cover all this segment. Okay? And when you go to the next generation, they still cover. So what does it mean? It means that the projection of the set onto this line, the orthogonal projection, doesn't look orthogonal there, but I assure you it is orthogonal. The orthogonal projection of this set will be a segment. So it has positive length. But the projection is a Lipschitz map. I mean, so as I said at some moment, Lipschitz map, the Hausdorff measure behaves nicely with respect to Lipschitz map. So the set couldn't be of 0 measure because otherwise its projection will have 0 length, and it doesn't. Okay? So this is true because there is at least one projection with positive length. Okay? So this is an example saying rectifiability is not just a matter of being finite measure. Okay? And I think this is, I plan to do the existence of tangent space, and I think I will do it. No, she will do it. Okay, so I was supposed to do the existence of the tangent, approximate tangent plane now, but I'm late and it's not possible. Okay, sorry for the overtime. Thank you.